Okay, students, welcome again. In this video, we are discussing about the alternate methods of E.M.F equations. Okay, you know very well if there are two different type of transformer existing in our system, electrical systems. If the K is nothing, it's a transformation ratio. K is greater than 1, it should be a step-up transformer, and K is less than 1, it should be a this is K is less than n1, or sorry, K is less than 1 or n2 is less than n1. That doesn't assume it's a step down transformer. Okay. Now the EMF equations of a transformer. This is alternate methods. Previous videos I am discussing about the EMF equations of a transformer, but in this video we are discussing about the alternate method of EMF equations of a transformer. So in this particular, we know the EMF equations, flux equations we know very well. The flux equations is phi equal to phi naught sine of omega t, and in this particular point this is alternating in nature. You know very well the time period of this particular waveform. I am indicating this at t. T nothing, it's a time period of this particular cycle here. This is t. Okay. Now in a half cycle it becomes t by 2. In a quarter cycle it becomes how much? This becomes a t by 4. Clear? Now at t, now we are considering a t will be equal to t1, or t1 will be equal to this is at t will t1 is equal to 0. Then what is the value of flux? It means at this particular point, at this particular point here, at at t equal to 0, what is the value of flux? Flux should be equal to, I am taking the flux phi 1, it should be equal to 0. And at t equal to t by 4 here, and t2 will be equal to t by 4, what is the value of flux? Phi 2 will be equal to phi naught. It means at t by 4, the flux should be a maximum value. The change in flux is delta f should be equal to phi 2 minus phi 1, and phi naught minus 0, it becomes a phi naught. And change in time delta t should be equal to t2 minus t1. This is t by 4 minus 0, it becomes a t by 4. So we know the average induced EMF in between 0 to a t by 4. So induced EMF E will be equal to here n d phi delta phi by delta t. So substituting the value of delta phi will be equal to how much? This is phi naught. And what is the value of delta t? Delta t is nothing, it's a t by 4. Clear? Now finally, what will have? E average should be equal to 4 n phi naught divided by t. You know very well the frequency should be equal to 1 upon t. The inverse of the time period is nothing, it's a frequency of the supply system. So what is the induced EMF? Then 1 upon t can be replaced by f. This is f. So here the E average should be equal to 4 n phi naught into f, because I am replacing 1 upon t is equal to f here. So in a sinusoidal, any sinusoidal waveform equations, the form factor should be equal to 1.11. This is the Kf value, the form factor of sinusoidal waveform. So because the flux equation is sinusoidal waveform, so form factor should be equal to which one? 1.11. So what is the form factor? Form factor should be equal to the RMS voltage to the average voltage. It is very well known formula. So what is the RMS voltage? I am ERMS should be represented by the capital E. So what is the RMS voltage? RMS voltage would be equal to 1.11 into E average, and we know the E average should be equal to 4 n phi naught into f, and you can multiply by 1.44, 1.11 multiplied by 4, it becomes 4.44 into n into phi naught into f. Now this is nothing, it's a induced voltage, a general induced voltage in any windings. So after substituting the value of n is replaced by n1, then you should obtain the induced voltage in the primary winding, that can be represented by E1. So E1 should be equal to 4.44 n phi naught into f, and E2 can be replaced by E2 will be equal to 4.44 n2 into phi naught. So it should be E2 divided by E1, it will be equal to N2 divided by N1 here. It should be equal to K. K is nothing, it's a transformation ratio of a transformer. So this is the alternate method of the induced voltage in a primary as well as in the secondary side. Okay, thank you.